Okay, I hope you are seeing the screen or the beside, I mean the PowerPoint. So we are going to talk about factors affecting persistence and efficacy of soil applied herbicides. There are, of course, there are two things. When we have applied our herbicides to the soil, we want to find out whether they will work, whether they will control weeds. If they control weeds, we also want to find out whether they don't have residual problems. We don't want these herbicides to stay too long in the soil so that they may interfere with our crop rotations. So what is persistence? It is the length of time the herbicide is present, probably being active in the soil. When it is desirable, we may want the herbicide probably to last for 3 to 4 months, so it can coincide with the critical period of weed control, so that it can suppress weed density to the extent that it is below the weed control threshold, and this can increase our yields. But if the persistence goes for 1 year, like what can happen to some of the trials in herbicides, then it becomes undesirable because it is going to interfere with our crop rotations. And indeed, when we are talking about soil applied herbicides, in most cases, we do pay attention to how long they stay within the environment. We want to know whether this herbicide may not affect crop rotations. Now, generally, the use of pesticides in agriculture has led to pollution problems. And one of the examples of the pesticide, although it's not a herbicide, was the DDT, which was quite, effective in reducing the mosquito and therefore lowering the incidences of malaria in this country. But the downside of it was that this pesticide had a long residual period within the environment. For example, it could be detected in water bodies, birds, as well as animals, and even in human milk, as was reported by Chikuni and Nachi, who were evaluating the presence of this herbicide. So probably there's this need to decrease or to carefully manage the use of pesticides. Probably you can hear some people now talking about the move towards organic farming. Now, the herbicides with a potential to be persistent in the environment, we have among the triazines, we have got atrazine and simazine, but atrazine, yes, we have got some reports on it in this country. Dinitroanilines, pendimethyl stomp, and trifluorine, phenylureas, diuron, yes, diuron can be very persistent, uracils, bromacil, or trichemical X. I think for uracil, its persistence is required because it is sprayed along railway lines. to control the vegetation along the railway tracks, and you want a long residual herbicide there. It's not a cropping field. Imidazolinones, imazapa, arsenal. Yes, that one can have a long persistence. Imazatapa, imazaquin, we were not sure whether we were having such problems. Even sulfonylureas, chlorimuron, classic, nicosulfuron, accent, then chromazone command. But definitely with atrazine, we have had some problems in Zimbabwe, and there has been some research to that effect. Now, what makes soil applied herbicides to stay in the soil depends on soil characteristics. We do have soils which are known as the montmorillonite clay minerals, the kaolinite clay minerals, which tend to attract these soil applied herbicides. Organic matter can also attract these herbicides because of the presence of the COOH and OH functional groups on the organic matter. But on the clay minerals, we may have positive charges on the clay minerals. Now, the presence of negatively charged surface can also attract some herbicides. Sometimes we talk of cation exchange capacity so that we have an indication of what can happen to the herbicide if it is soil applied, because it is reacting with the soil. When we talk of efficacy, this is the effectiveness of the herbicide in controlling the weeds. For example, we can have good weed control, which is desirable. We can also have poor weed control, which is undesirable, after applying these herbicides. So spraying is done directly to the soil for pre-emergence herbicides. And you can see that the pesticide or the herbicide is going to react with the soil. So the question is, what will happen to soil applied herbicides after spraying? Right? In order to answer these questions, we need to understand about 7 processes which can happen to the herbicide after it has been applied to the soil. So some of these things are: the herbicide can be lost through leaching. It can travel downwards in the soil, depending on its physical characteristics. Number 2, it can simply be lost in the atmosphere. This is a function of its physical characteristic known as the vapor pressure. So it can be easily be lost. Number 3, in the soil we do have microbes with the capacity to break down these herbicides. They use enzymes. They are also endowed with the enzymes like cytochrome P450. They may also have the glutathiones, which can conjugate these pesticides. They also have glucose, which can also participate. In fact, all what we talked about under selectivity, about phase 1, phase 2, phase 3, can also occur under microbiological breakdown, which is number 3. It is also similar to the plants. They can translocate the herbicides if they have been soil applied via the xylem vessels, and these herbicides will eventually reach the plant cells, where they will again be broken down using the phase 1, which involves cytochrome P450, and the phase 2, which mainly involve glucose and the glutathione. And also this amino acid may be involved. Then phase 3 may also involve malonyl addition and glucose addition, all of those things which we discussed. So you can see this is a long process of herbicide breakdown, either in plants, number 4, or in microbes, number 3. But the processes are more or less the same. But there may not be phase 3 in some of the microbes. Right. So we go to the soil characteristics, whether we have got clay soil, sandy soil, but here we are mainly concerned about the clay content, which plays a big role in actually it may attract these herbicides to the extent that they may not be available, or they may break down at a fast rate. So that is number 5. Then number 6, we have the effect of sunlight. Now, sunlight may affect certain herbicides. Containing nitrogen and carbon. In other words, light makes those molecules excited. After excitation, then there's breakdown. You can have all these oxidation, reduction taking place, or even hydrolysis in the absence of enzymes, but being facilitated by the sun. So the herbicide on the soil surface is vulnerable to breaking down. There can also be chemical composition, chemical breakdown. These are simply chemical reactions, test tube type of reactions where no enzymes are involved. It's a simple reaction like that. Oxidation, it may be reduction, it may be hydrolysis, and this can actually cause the herbicides to break down. So you can see that we do have 7 processes. If you have applied your herbicide at the recommended rate, the herbicide which will finally kill the weeds could be a very small amount. The rest could be lost through various processes. So we are going to talk about these various processes. But before we move on, as far as 3 microbial breakdown is concerned, and the 4 herbicide breakdown in plants is concerned, I'm not going to waste time on those issues because we discussed them at length yesterday. So I don't want to repeat the whole process, although I have given some short notes under this persistence. So let's move on to talk. In fact, these 7 processes, we can divide them into groups. There are those processes which are physical processes. For example, leaching. This is it's just a physical process. You apply the herbicide on the soil surface. What is important after applying the herbicide on the soil surface is the property of the herbicide known as the solubility, which is the degree to which that herbicide is soluble or is dissolved in water. Solubility is measured in parts per million, ppm. And here we've got examples of herbicides with their corresponding parts per million. On top of the list, we have got dicamba, which is highly soluble. You apply it to the soil, dicamba may end up in drinking water. It can travel very far, downwards, until it reaches the water table. It has a solubility of 720,000 parts per million. In contrast to pendimethalin with 0.275 parts per million. So pendimethalin will actually sit on the soil surface. It can hardly move. No wonder why we exploit its solubility in depth protection. Because if you plant your maize, below the zone of weeds, you can achieve selectivity. Even the dicamba with 11,000 parts per million, we can also exploit it. It's not highly soluble. It's not highly soluble. So the high solubility, it means available in the soil solution and is likely to be reached, like dicamba. But sometimes we want solubility because we want to leach the herbicide to the weed zone, preferably. But if leaching goes beyond the weed zone, then it may start killing our crop. If it goes beyond the crop depth, then it becomes pollution because it will reach the water table. So basically, leaching is the movement of the herbicide downwards through the soil profile. It is desirable when it takes the herbicide to the weed zone, and we can achieve positional selectivity or depth protection like what we do with the Sengo, metribuzin, or pendimethalin. This becomes undesirable when the herbicide reaches the crop root zone and we can lose selectivity. And indeed, sometimes it can happen with metribuzin. After heavy rainfall, the herbicide is reached to the soybean crop, which becomes damaged. Just reminding you about the positional selectivity or depth protection. It is exploiting the solubility characteristic of the herbicides. So there are certain herbicides which we can exploit their physical characteristic in terms of leaching, and then we can protect our crops. But of course, in the case of metribuzin, after heavy rains, it may be leached. So amount and factors affecting leaching, this could be amount and intensity of rainfall, soil texture, amount of clay and organic matter. An adsorbed herbicide is available for leaching. Then ionization properties of the herbicide, it can be positively charged herbicide. Uh, then the herbicide is less likely to be leached. The herbicide loss, we can have surface runoff, which may depend on the rainfall amount, rainfall intensity, and the erodibility of the soil. So what we are saying that if our soils are not properly conserved, soil erosion can make herbicides to be lost, and they may actually kill certain plants outside the herbicide application area. This is another aspect. But with leaching, sometimes it's desirable. It can bring about selectivity in some herbicides, but in some cases, it can lead to pollution. If you want to test the leaching of herbicides, you can use cylinders, right? Now, what you do, these cylinders should have some holes where you plant sensitive crops on the side. First, you make them upright and apply your herbicide. You allow the herbicide to reach after 2 days or 3 days. Then you put the tubes in a horizontal position. Then you plant a sensitive crop like cowpeas in this case. I think in this experiment, this was sandy soil, which allowed most of the leaching. In fact, the herbicide was lost. That's why this crop is thriving, because there is no herbicide there. So, in fact, we have this one is the control. Sorry, this one in the background is the control where no herbicide was reached. This one is where atrazine was reached, but this is sandy soil. So sandy soil allowed the herbicide to be lost. But in the case of heavy soils, this is the control. The heavy soil tended to retain the herbicide, and it killed, this sensitive crop. You can see nothing, on the holes. It was a clear demonstration that the clay soils could retain the herbicides, and then they can actually cause residual problems. Number two, volatilization, that is the loss of herbicides after spraying them to the soil. They can be lost in the atmosphere through a process known as volatilization. It is the physical change of a herbicide from solid or liquid to gas. 80 to 90% of the herbicide can be lost within a few days after application. Volatilization depends on vapor pressure. Examples of herbicides with the high vapor pressure are EPTC, trifluralin, and the command chromosome, which is used in tobacco. Well, these are the vapor pressures of the herbicides with a potential to be lost via volatilization. In some cases, uh, the formulation of the herbicide, like 2,4-D, it may cause it to be easily lost through volatilization. Even atrazine can also be lost through volatilization. Now, because of this issue, EPTC and trifluorine, if you spray them, it is recommended that they have to be incorporated in the soil. What we call pre-plant incorporation to avoid the loss via volatilization. You do it under dry conditions. When you irrigate, the herbicide becomes available to kill the weeds. So soil moisture displaces EPTC from adsorption sites, then it becomes available to kill the weeds. But if you spray it under moist conditions, then you will lose most of it because it's not going to remain in the soil, because it can only get absorbed under dry conditions. 2,4-D is capable of drifting from the point of application. Hence, it can affect crops off target. So some herbicides with low vapor pressure could be affected by volatilization. Now, this is the case for 2,4-D drift. You've got farmer A who is applying the herbicide. Then the herbicide vaporizes and it is carried by the wind and is eventually deposited to farmer B, and the crop may get injured. It's not intended, but it's because of the physical characteristics of this herbicide. So we have dealt with physical processes, which are two. Biological processes. In the biological processes, we are talking the role of plants and microorganisms, which have enzymes which can transform herbicides. It is the major route of herbicide detoxification in the environment. We now know that metabolism of herbicides involves three phases. We've got phase 1, phase 2, and phase 3. Here, I'm not going to go through again the whole process. I'll assume you now know what is phase 1, what is phase 2, and what is phase 3, so that we don't waste time on this. We all talked about this yesterday. What I will just say here is that when plants die, further degradation may take place due to microorganisms. And some of these herbicides may be turned into nitrogen or carbon dioxide as the final breakdown after having gone through these phases, which can occur in microorganisms or plants. But let us talk about what can happen to 2,4-D under under the breakdown of microbes. Now, microbes may not have the enzymes to degrade 2,4-D. So if you apply 2,4-D to the soil, the microorganisms in the soil appear not to be degrading 2,4-D for a couple of days or even months after they come into contact with the herbicide. Probably during this period, once the microbes sense that there's something in the environment, they will start to synthesize appropriate enzymes which are needed to degrade this herbicide. So, first season, your herbicide may work very well. In the second season, you may find that the herbicide could disappear rapidly because the microbes have now acquired the necessary enzymes which can break down these herbicides. For instance, they could lack cytochrome P450. Then they have to acquire these enzymes in the next generations. Then when you apply 2,4-D, then most of the populations of microbes will be carrying a cytochrome P450, and in phase 1, they will start to degrade this herbicide. So future application of 2,4-D could be accompanied by rapid degradation, meaning that the population which is now existing in the environment is now acquired these enzymes. In USA, there are some places where herbicides do not work simply because of rapid degradation due to microbes. There are also some microbes which can convert MCPB and 2,4-DB via beta oxidation to MCPA and 2,4-D. They make these substances toxic. We have got Pseudomonas species, Micrococcus species, and the Aspergillus niger, which can activate, we call it microbial activation. This can also take place in a plant. And if it is a plant, the plant may actually die because of herbicide toxicity. So if we are talking of biological processes, we are talking about plants and microorganisms. And the main issues there are phase 1, phase 2, and phase 3 is the key drivers in herbicide breakdown. So we move on to non-biological processes. Here we are interested in the soil, especially clay minerals. Probably at this stage we should go to the basics, where we are going to say ions and molecules are electrically attracted to colloidal surfaces. So what we are saying is that herbicides with ions or with some molecules, they may be attracted to clay minerals. However, the herbicide needs to be in an ionized state in order for it to be adsorbed or attracted to the clay minerals. When we say in an ionized state, we are saying it should display either positive charges or negative charges. The adsorption of the herbicide ions and molecules occurs on the clay and the organic matter surfaces. So what is critical here in the soil? The amount of clay, especially in this part of the world. It is the clay content which matters. Organic matter, I mean, in our soils, they've got very little organic matter. So we do not usually consider it to be important in the tropics. But if you are in Europe, US, in the temperate climates, yes, the soils have got high content of organic matter, and that can influence the herbicides. So what can happen is that if we apply the herbicide to the soil, part of the herbicide is going to be absorbed by clay or organic matter to saturation point. And whatever is no longer being absorbed is the one which is available to kill the plant or for microbial action. Later on, probably I will have to talk about this clay content. We use it to calibrate the dosages for pre-emergence herbicides. Because you'll find that for different soils, we have got different rates. It's because of different amounts of clay content. There's a process known as desorption. It is the movement of herbicide ions from clay and organic surface into the solution. The reverse is what is known as adsorption. So we have adsorption and desorption being in a state of equilibrium soon after applying our pre-emergency herbicides. Because some herbicides are adsorbed, others are in the solution. So we can actually use this diagram to illustrate adsorption and desorption. When we talk of adsorption, let's say we have got a clay particle, it is attracting the positively charged herbicide or ionized herbicide on its surface. Now, when this surface is now full of herbicide ions, some are left free in the solution, or they can move into the solution through desorption. So you have constantly some hello Maniro azvi ndabuda ndabuda rini ndaitaura nezvichi baba ndobva ndabva ndabuda ipapo dzanguva ikweyo zvino saka chiregai tigokontinya mangwana handitika chiisa meseji ndinotofunga kuti ndine vanhu ini ndachitotaura kai Yeah, chisa message. Okay.